and for temperature measurements, how many of the molecules are in the various states. And that is given by the Boltzmann distribution. So the population, the number of molecules in the different vibrational states is given by this expression, where this is constant for the molecule that you can find in textbook, divided by Boltzmann constant and T. And here you see, this is the parameter that we want to extract. So if we take for N2, to look at how many molecules, this is the fractional population. If we start at the low temperature, you see that we have almost all in the ground state, and then this goes down, and at the same time the population in the higher states get populated. And that means that by probing the different states, we can directly measure the temperature. But then it gets a little bit more complicated, as I said. They are not only vibrating, they are rotating. The molecules are rotating. And they can rotate slow or fast. And that is also giving information about the temperature. And that gives a substructure. So we started up with one electronic state. Then we divided into vibrational states, and now we also have a substructure of rotational states. So for each vibrational state you have a substructure, and also there you want to know how many of the molecules are in the different rotational states. And here is once again how it looks for nitrogen at 300 Kelvin and at 700 Kelvin. And these are the individual transitions. That is odd here, it depends on the nuclear spin, which I don't have to go into. And I think the most important here, you don't have to understand all of this, but you just have to see that what we are using is the difference in population. You can see that this is completely different as compared to this. That is how we measure temperature. And it might, if you haven't seen this before, it might look very strange, very odd, very complicated. But this is not, I mean, deep physics, I would say. It's just knowing the energy levels, knowing the Boltzmann distribution. You have the rotational constant, rotational quantum number. You have a specific rotational constant, specific for each molecule. You can look it up. I mean, it is well known. And here again, you have, this is Planck constant, speed of light, and you have the temperature. So this is, I mean, you can do it in 2 minutes to get calculation on how the different species look like if you plug in the constant for different molecules. So this was just very short how the molecules are constituted and how you can get different temperatures. So here you have the population in the ground state. It's pretty narrow at low temperature. Then when you go to higher state, this is broadened and you get additional band from this higher lying level. And this is exactly how we measure. This is our spectra. We fit the spectra to a temperature with temperature as a fitting parameter, and then we can get the temperature. Not I would say, too deep science, but if you haven't seen it before, my experience is that this might look very, very strange, but it's not that difficult. So with that, I will leave the background, but now at least you know that we have structures in the molecules which we are using. And then when I come back to laser-induced fluorescence, we have to sort of fit exactly with our wavelength. Okay. So then the next is to describe a little bit about the equipment. We need a lot of equipment to do this kind of experiments. We have to have a laser system. There are a lot of different lasers. We have to have a lot of optics, lenses, polarizers, filters, mirror. We have to have a detector. This is a setup for incoherent scattering. We have the laser beam. It's formed by a lens focused into the chamber. We focus the laser beam with a lens through optical filter onto a detector. And the detector could be a CCD camera. It could be directly, or it could be a CCD camera followed after a spectrometer, or it could be a photomultiplier. So I will briefly describe this. I don't know how much you know about laser. What is a laser? Why do we have laser action? Well, laser stands for light amplification by stimulated emission of radiation. It gave the Nobel Prize in the early 60s. And very, very briefly, if you have a medium, an ordinary medium, it would be a solid medium, it could be a gas, it could be a liquid. And then we have a system. This system, for example, a gas. And I said before, we have energy levels where the difference is given by Planck's constant times the frequency. Essentially, this has at a certain wavelength. And normally you have, according to the Boltzmann distribution, a lot of molecules in the ground state, very few in the excited state. That's how normal sort of media looks like. And if you send a laser beam or light through this, then you, and on resonance, I mean, that fits with this splitting. You go through the medium, and if you have maybe 4 photons here, you get 1 photon out. That's simple absorption, right? But what will happen now if we, for some reason, disturb this medium? We disturb it very strongly so that we have more photons in the higher state than in the ground state. And that could be done with a flash lamp, it could be done with electrical discharge, but we essentially make it highly non-thermal. So actually what we are saying is that we have negative temperature. What will happen then if we send in a beam or a photon exactly corresponding to this? Well, in this case it was attenuated, we got absorption. But now instead we got an amplification. So 1 photon comes in. If this medium is in this state, it's amplified so that we'll get 3 photons out. Right? And what will now happen if we just put a mirror here and there? Then this will go back and forth a lot of times. Every time it will get amplified at this specific wavelength. And then we make one of the mirrors partly transparent. So it goes back and forth quite a bit. Then we'll get a very, very strong signal at a specific wavelength corresponding to this energy level diagram, and with a very direct, as it comes out as a laser beam. So, I mean, this of course is much more complicated, but it's sort of a hand-waving way to describe how you create a laser. And the nice thing with the laser is that it's monochromatic, means that you have a very, very narrow line width. It's coherent, meaning that the photons coming out are in phase. Some of them can be tunable. This laser, for example, is at 532 nanometers. It cannot be changed. You cannot tune it. They are highly directional. You can see, I mean, I can send this 10 meters or even more. I mean, it's just get a slight divergence. The lasers can be continuous wave or pulsed. This is a continuous wave laser. The pulsed laser that I will describe later has pulse length on the order of nanoseconds. it could be femtoseconds or even attoseconds. Very, very, very short pulses. Nanoseconds is 10 to the minus 9, femtoseconds 10 to the minus 15, and attoseconds 10 to the minus 18 seconds. And you can have a very high energy, and for laser diagnostics it's important to go up to joules. Just a couple of words on safety. This is extremely important. We're working with lasers that have very, very high peak power. The peak power, the energy is maybe not that high, but since the pulse length is very short, the energy, the peak power is very high. It could be megawatt. So we could have like a nuclear power station running in 10 nanoseconds. So just imagine that and all of this goes into this beam. And then of course, if this hits your eye or even a reflex of this, then it's destroyed. It's totally destroyed. And fortunately, in our division, we have worked with this since late 70s. We haven't had any accident, but I have several colleagues around the world that I got their eyes damaged. So this is very, very important. And when we have this, we have strict rules that nobody should by accident come into the lab. I mean, you have to lock the door, you have to have signs, and you should only go in there when you have some guide to help you. So this is really important. Okay, I will just briefly mention the main laser that has been used is YAG laser. 90% of combustion diagnostics are using lamp laser, YAG lasers. And here you can recognize, here you have, in this case it's a solid state laser, meaning that the laser medium is solid laser rod. And then you have the output mirror, end mirror. And once again, I mean, you pump this, you excite this species or molecules in the laser rod by an external discharge, a pump lamp, to get this sort of abnormal state. And then you get out on the order of 5 to 10 nanoseconds. You can have different wavelengths. Normally 532 is used. You can get quite a lot of energy, 500 millijoule, 1 joule, but as I said, the peak power is on the order of megawatt. The repetition rate on the order of 10 to 20 hertz, and there are a lot of companies selling this. Then we have a problem, right? I mean, this laser is more or less useless for laser-induced fluorescence. We have to have a tunable laser. And how could we achieve a tunable laser? Well, I'll try to guide you. If we have a media like this, then we have an end mirror, output mirror, so the beam will come out like this. Then if we choose a medium that has a broad absorption and a broad emission. In the previous case, in the YAG laser, it's only discrete values. But if we, for example, choose dye solution, this has the nice feature that the energy levels are very, very, very close, so that you get a continuum, a broad continuum. So here we have dye in a liquid, and then we illuminate this with another laser at for example, 532 nanometer. Then we'll create population inversion in these molecules and the output beam will not be, as in the egg laser, like this narrow, but rather we'll get something that is broad, right? It could be hundreds of nanometers or angstroms. So now we have a broad laser. Instead of a narrow laser, we have a broad laser. But that's not what we want. We want to have a tunable laser. But what would now happen if we here put, instead of a mirror, something that will, so the laser comes here, and then we want to have something that only reflects a certain wavelength. So that the broad laser comes here, and then it's split up into the different colors. So that different colors will go like this. It's like a prism. So this is broadband, and then this device, which I will define later, reflects the different wavelengths in different directions. Right? Then it happens to be that, of course, one of these wavelengths fulfill the condition to go back and forth. So now, with this setup, one of these wavelengths comes out. But then if I turn this a little bit, then another wavelength will come out. And this is called a grating. So this was shown in the 70s, that if you replace the totally reflecting mirror with a grating, then you can, just by tuning this, then you can change the wavelength. You have a narrow wavelength that you can tune. And this is sort of shown in this, essentially the same as I have written on the table. So this is very, very useful. It's a necessity when you want to do most of the work I will describe. Because here you can change the wavelength. And I said that you use a dye. Here you have the dye cell there or here. And then these are commercially available. I mean, you have, here is one dye going between 410 and 430 nanometer. Here is another dye going from 620 to 670. So you just choose which dye you want to use, and then you can get tunability, narrow line width, from in the whole visible region. And this is, so you just buy, for example, a rhodomine dye, dissolve it in ethanol or methanol, put it into the dye cell, illuminate with another laser, and then you have the tunability. Then sometimes you want to, I showed this picture also, want to make high-speed measurements, and this is the multi-YAG system we have constructed in Lund, which can produce 8 pulses at the same time. It looks pretty complicated, a lot of optics in it. That is when we want to make high-speed measurements. And then you also can do this nowadays with kilohertz lasers, which is used for good for when you study transient phenomena, ignition, extinction, misfire, and flashback. And as I said yesterday, the price you have to pay here is that the pulse energy is much lower. And then, fortunately, recently there is another very high power laser, which is called a burst mode laser, where you can get a frequency up to 100 kilohertz with up to 1,000 pulses. So this is, I would say, right now the most advanced laser for diagnostics. Then switching to detectors. Detectors are, of course, very important. Now we hopefully know that we have a tunable laser. Then we have to have a detector, a very sensitive detector. And the most sensitive detector is what is called a photomultiplier. This is, you have the incident light. This is a photomultiplier. The incident light, the light is hitting a photocathode. You generate electrons, and they are amplified in what is called a dynode chain. So from one photon, you generate a lot of electrons. So this device can almost detect single photons. It's a very, very sensitive detector. And this can also be used together with an oscilloscope to measure very short time scales. So that I would say when I did my PhD and started, that was the detector to use. Then in the 70s, we got intensified charged copper device, ICCDs. And you know what, CCD, that's what you have in your mobile, right? This is similar, but it's consists also of a gated intensifier. So this gated intensified CCD is maybe 1,000 times more sensitive as your mobile camera, but unfortunately also maybe 1,000 times more expensive. But this is what is used in a lot of this two-dimensional imaging. And here you have the MCP multi-channel plate where the photons comes in this channel, and in a similar way as in the photomultiplier, it goes and hit the walls, generate secondary electrons, and then this is transferred and hit the either directly or by lens coupling, fiber coupling to a CCD. So here you have the two-dimensional CCD. In front of that you have the intensifier. And why do we need an intensifier? Why? First of all, of course, we intensify the signals. We increase the signal strength. But maybe the two other reasons why this is very important is that whereas in a normal CCD, you cannot gate the detector. You cannot sort of you can have a shutter, but if you are using your camera, your mobile, and looking into a flame, then of course, I mean, you get a lot of photons from the flame. But I only want to have photons from when my laser is on. Remember, my laser is 10 nanoseconds. That's when I want to collect my light. I'm not interested in what happened outside this time window. So if I have a luminous flame, I will get too many photons from the background. So I have to use something to gate, to activate the photons and the detector. So this can be gated, meaning that we say that this is only active when the laser is on for 10 nanoseconds. Otherwise it's blocked. And then we can suppress the background radiation from the flame. That's one very important reason. Another is that your mobile camera is not sensitive in the UV. And we want to make a lot of experiments in the UV region. This is UV sensitive. So this transforms UV light into visible. So we can go down to 200 nanometers. So there are three real important reasons why we want to have a multi-channel plate. Intensify the signal, it works as a gating, and you increase the detection wavelength range. Then when we want to do high-speed measurements, we want to be even more advanced. We want to have framing camera. Framing camera is a camera which can take images extremely fast. Normal camera runs at maybe 100, 200, up to maybe 500 hertz. This can go up to megahertz. It can take a lot of images. Well, not a lot of images, but images very close in time. So we have been able to buy such systems, and in this device it was limited to 8 images. It could take 8 images very short in time, essentially down to a nanosecond difference, and it works as the light comes in with this lens system, then it's divided into different 8 individual gateable CCD detectors. So we divide the image into 8 individual, and then we can gate them sequentially and follow extremely fast phenomena. And of course, if you remember, the laser system we built could produce 8 pulses, and by accident this could take 8 images. So then we have a laser system producing 8 pulses and a camera capturing 8 pulses, and then we can measure very, very fast. Then there are nowadays also high-speed cameras that can be used, not maybe as fast as the framing camera, but sufficient up to 10 kilohertz and higher. So these are now used to measure fast events when you have a high-speed camera. When you are looking into a CCD camera, it's important to have a high dynamic range, meaning that you are able to measure both small and high intensities. The efficiency should be high, the quantum efficiency. That means the conversion of photons to charges. The sensitivity, you can choose whether you want to have a high sensitivity in the UV, in the visible, or in the infrared. The readout time is important. And sometimes when you want to increase the sensitivity, you can, instead of reading out each pixel, you can combine pixels by what is called binning. So you put together 2 times 2, 4 pixels into one big sort of super pixel. Normally each pixel is on the order of 10, 20 microns. So that means that we maybe have 50 microns times 50 micron. That's the size of each pixel. Then when we do diagnostics, we have a lot of optics. I'll just briefly mention something. I mean, we can have polarizers. Optical filters are very important. We have different lenses, prisms, and also spherical lenses. One important part is, for example, dichroic mirrors. That means that if we, for example, in some techniques, we want to overlap beams, or want to distinguish, when we have a laser, we have 532 and 106 on top of each other. And then we want to separate the 532 from the 106. Then we have a special mirror, which is called a dichroic mirror, that reflects the green beam, transmit the infrared. In cars, we want to combine one red beam and one green beam. That can also be done in a special mirror, where this mirror transmits the red beam and reflects the green beam. So we get these beams overlapping. And remember now that this beam has a very high energy. So this has to be coated in such a way that it can stand the laser energy. Otherwise, you destroy the optics. In the beginning, when we got this high power laser, we destroyed a lot of optics. Interference filter is a filter which is only transmitting at a certain wavelength. And of course, if we want to do laser-induced fluorescence, we know that the emission will be, you remember the C2 had a certain lines. Then we have to have a filter to help the detector to suppress the background. So this filter is only transmitting at a certain wavelength. It looks like that. Then, of course, you have to be careful with window materials. If you want to do experiments in an optical engine, in a gas turbine, you can't use ordinary glass because that won't transmit. So you have to look for what is the transmission characteristics of the material. And that's why we normally use quartz, high quality quartz that goes down to 200 nanometers. So if you try to do an experiment in a cell and measure, for example, NO that absorbs at 200 nanometers, you wouldn't have a chance with ordinary glass. This is something that you have to watch for. And then prism. You can use prism for various actions. You can have it to polarize the light. You can separate beams at different wavelengths. You can reflect the beam. I mean, if a beam comes in like this, I mean, you have a total reflection in this side and then it goes in this direction. And then finally, you maybe have heard that I've described spectrometers, spectrographs. And that is a device. It comes as a box. And in this box you have an entrance slit and an exit slit. So your light, that could be whatever light, sunlight or from the flame, is focused onto the entrance slit. Then it goes into a spherical mirror and it hits this, you remember the grating, this device which divides the colors into different directions. And that means that the light goes like this, and then you get a certain wavelength coming out. And by changing the angle, you get another wavelength. So if you have white light here, it comes in, then you will get a rainbow on the outside. And then if you have a detector, scan this, then you will get a spectrum. Or if you remove the slit and put a two-dimensional detector, you will get the spectra directly. And these are commercially available, and you can also build them. I mean, it's not that difficult. You just have a big box. You have a slit. You have two spherical mirrors and a grating. Then you can sort of build your own spectrograph or spectrometer. Okay, I think we can maybe, you said that we should go to 11 or?
No, it's time for break.
It's time for break? Okay. So far, now you sort of have the base, hopefully. Next time we'll go for laser-induced fluorescence application and Rayleigh-Raman scattering, and if time permits, also some cars and so. But are there any specific questions on what we have described so far? Or is everything clear? Yes?
I have a question about the window.
Window, yes.
Yeah, as you see our burner in our labs, we don't have laser or something like that. We only do direct photography.
Yes.
The window or the quartz is effective as or photography or using.
Yeah. I mean, quartz is as you already realized, much better in terms of standing heat. If you go for Pyrex or whatever, I mean that wouldn't hold. But I mean, quartz is also much more expensive than ordinary glass. So whenever you can use glass, I mean, I would maybe go for that. But it depends on your application. It's in terms of standing heat, standing stress, things like that. But for ordinary measurements in the visible, it doesn't matter. I mean, quartz and glass are the same between 400 and 800 nanometers. So if you want to sort of look for the chemiluminescence from a detection point of view, you can equally well use ordinary glass. Yes?
Thank you very much, Marcus. I have a question regarding the resolution, the time resolution that you
Yes.
want to take capture the capture the how to say that eclipse or the how to say
The time resolution of the detector.
detector exactly.
Yes, yes.
The point is, it depends on the physics of the problem that you want to solve.
Yes,
Am I right?
yeah, right. I mean, so I mean, you shouldn't go for a nanosecond or picosecond if you don't need that. I mean, since we are working in the nanoseconds, I mean, very often we need the high temporal resolution. If we want to resolve the fluorescence decay that is in sub-nanoseconds, of course, we need a very high temporal resolved detector. But I would say that if you do not have the temporal requirement, why should you buy something that
So the question that comes to my mind is that the physics, for example, the detonation
Yeah.
needs such high resolution and time resolution.
Right.
When it goes to usual combustion, it's usually pulsations that are important.
Yes.
Pulsations have like less than nanoseconds.
Yeah, you are in the kilo or millisecond range, I guess. Yeah.
So what you are using here is mostly for detonation and ignition. That is very important. Am I right? I'm asking about the examples of what a person should keep in mind when you're talking about such time resolutions. Is it other than that?
Well, I mean, when you buy your detector, I mean, that goes into the specification. What's the rise time? And I mean, since we have been working with irrespectively of the combustion phenomena, since we are working with nanosecond lasers, we want to have a temporal resolution that is adequate for the pulse of the laser. But if you are just looking for phenomena, I mean, go into the specification sheet and don't pay for more than what you need. But we are sort of driven not by the phenomena we are studying. We are driven by the pulse we are using.
So you're developing these technologies. For that, you need different resolution.
Yes.
For
yes.
me, as a user of
Yeah.
combustion science, maybe it's not important.
Then you should definitely not overkill your sort of capability. So I think you might have a different application in mind than what we have. Yes.
I have a question regarding the dusty flames.
Dusty flames. Yes.
Yeah, if you have a kind of industrial combustion, like a flame that you have like torrefied biomass or biomass as a
Yes.
kind of a solid fuel,
Yes.
how we can set and use this method, or like if you have a kind of fluidized bed combustion, it's completely chaos. You don't know where you should set your laser and how this laser can help you
Yeah.
detect what you want to learn from this laser.
Yeah. If you want to use lasers, of course, I mean you have to face the situation you're looking for. I mean, if you go into a fluidized bed, I mean that's I would say one of the worst you can think of, because you have a lot of things that could go wrong. And I've discussed with the colleagues at Chalmers, you know, with having this fluidized bed and for the lasers to be useful, I mean, you have to be able to go through. Because I mean, you run into this with the multiple scattering and actually we did experiments many years ago with cars in a coal fired boiler, where the transmission was on the order of 5% through the furnace, but still we could get a signal. So I would say that you just have to try. I mean, I wouldn't say that technique would work. I would say that it might work, or you might run into trouble. You might solve the problems, but each sort of this phenomena is unique, and depending on what kind of parameters you want to measure, I think you just have to try. I mean, it's so far this technique have not been used extremely much in that harsh environment. I mean, we have done experiments in engines, gas turbines, We started looking into biomass, but not sort of a maybe a fluidized bed.
It means that it's not applied for the kind of district heating purposes that you are using in Sweden. For instance, you have like a kind of municipal solid waste,
Yeah.
and you create the heat from this municipal solid waste, and it's very hard to get the proximate and ultimate analysis of this
Mm.
at the first point, and even how is it possible we don't know anything with this advanced method.
Just simple, this one very small.
Mm.
They use in fluidized bed, they use these 2D cold furnaces,
Yeah.
and they use this optical method that's very important. I mean, they lose something about three-dimensionality when this laser and optics, especially the phosphorus ones that you talked about yesterday.
Yeah. Yeah.
It's very important to track the particles when it comes to the furnace, and then how does it go up and
Yeah.
down and so
Yeah.
on.
Yeah.
So I mean, fluidized beds also use some optics that are very important.
Yeah.
to develop.
The problem, as I see it, is that when you can't go through, I mean, I've discussed with people doing fluidized bed, and if the beam doesn't go through, I mean, then you have a problem, and then still, I mean, you can look at a technique like ballistic imaging is a technique which are used in dense sprays, where you look at the sort of the photons first coming out. And that is, I won't occupy you, but I mean, in principle, no, this. With a red beam, I mean, if I would illuminate my finger with a red beam, you would have seen the red light, right? But you wouldn't have seen the bone. Why wouldn't you see the bone? Well, because you have so much multiple scattering. But if you use a very, very fast laser, a femtosecond laser, the first photons that do go through without multiple scattering will be detected. And this is the technique that has been used quite a lot in dense sprays. And maybe that could also be used in fluidized bed. So there are techniques, but then you go into very, very advanced systems which hasn't been applied there yet. So I'm not saying that it's impossible. I'm saying that so far most of the work has been done in pretty clean flame, sooty flame. But if you go to furnaces and real application, that's still a challenge. Okay.
Okay, thank you. Time for break. After 15 minutes. Thank you. Okay, thank you. Very good speech.
Good.